Welcome back, viewers. So we were discussing about convolution, and particularly we were looking at an example of a rocket under some idealistic assumption. So we assumed initially that the rocket has a jet engine behind it, and when the engine is ignited, it throws out some amount of gas at high pressure, and by virtue of Newton's third law, the reaction force of that gas pulls or pushes the rocket forward. We also mentioned that if during a burst some amount of gas is thrown out, then the velocity caused by that burst looks like this. So the x-axis here is the time axis and y-axis is the velocity. So this is velocity and this is time. This is velocity. Okay, and this is the instance when the rocket is ignited. So the velocity instantaneously goes up and then comes down slowly due to the opposition offered by the air friction. Okay, and we also say that this is called an impulse response. Because this is how the rocket responds against the impulsive force generated by the gas thrown out from the jet engine. Okay, and then we discussed how the velocity to be computed at any instance if I know the instances where the rocket is ignited. If these are the instances when the gas is thrown out from the back, then depending on the amount of gas being thrown out, each will cause a velocity profile like this. Their individual heights depends on the amount of gas being thrown out. So here the height is lower, which means the amount of gas which is thrown out is lesser than the amount of gas which is thrown out here. Then again, another impulse response, and if we sum up all these individual impulse responses over time, then this is the sum. Then here it goes up higher, then comes down, then here it goes up higher further, comes down, up and down. So this is the velocity of the rocket at any instance of time. So this is time axis, this is again velocity axis. Okay, so this is how we can find the velocity at any instance using a graphical method. Today we are going to look at another alternative graphical method for finding the velocity under such situations. So let me call this as graphical method 1. Graphical method 1, and today we are going to discuss graphical method 2. In method 1 we have considered individual rocket ignition separately. So we have considered first this is called the burst 1, here is the burst 2, burst 3, and so on. and we have considered them separately and individually. So we considered first burst 1 and have drawn the velocity profile or impulse response generated by this burst 1. Then we have considered burst 2 separately and have drawn the impulse response caused by burst 2 alone. Then we have drawn the impulse response generated or caused by burst 3 alone. So we have considered them separately, individually, and then have added up this individual impulse response. Today we are going to discuss another method which we are going to call as the graphical method 2, where we will consider individual time instance separately. So what do I mean by that is as follows. In graphical method 1, we get the velocity at any time or at all the time instances finally together. Okay, so after we add up these individual curves, then we get the velocity at all the instances of time simultaneously, right? But suppose I want to know only the velocity at this instance, right? In that case, it's obvious that I need not consider the impulse response at all for this burst 2, 3, 4 or so on. We can only consider burst 1 because only burst 1 is responsible for generating the velocity at this instance. Similarly, if I am interested in only in the velocity at this instance, at this point, then I have to consider only the effect of burst 1, 2 and 3, but not 4 and so on, right? So if I am interested only at a particular instance of time, I need not draw the impulse response for all the individual bursts and add them up. That is redundant. That is more than necessary, because I am interested only about the velocity at a particular instance of time and not for all instances of time. Under those situations, the method that we are going to discuss today, the graphical method 2, is more efficient or easier to use than graphical method 1. So this is how we'll do it, graphical method 2. So graphical method 2. Okay, so we will first draw two curves, one for the excitation. So here we will draw an impulsive excitation which corresponds to burst 1. Then here burst 2, this is of lower height because here we have seen that the amount of gas thrown out is lower. So this is the impulse corresponding to the burst 2. This is the second excitation. Here we have the third excitation. Here we have the fourth excitation. So this is the excitation curve over time, right? And so this is time, and this is excitation, or in other words is the mass of gas per unit time, or the rate of gas being exhausted per unit time. So this is the excitation curve, and now we will find the response curve or velocity curve. How? For that, we again need this impulse response. Now what we will do, we will make a replica of this as follows. Let me prepare that and come back. Okay, so I have the impulse response copied on a separate piece of paper now, like this. So this is how the impulse response looks like. This is time and this is the height is the velocity. So what we see, so this impulse response tells me that if here unit amount of impulsive force is generated at t equals say 0, so at t equals 0, if the velocity, if the impulsive force generated is or not the force but the moment of force is 1, then the velocity here becomes say v, say this point is v, this height is v, then say here the height is v by 2, right? Let me draw it bigger like this. Okay, so here it's v, then at some point of time I have something like maybe v by 2, then here I may have v by 4, here I may have something like 3v by 2, and so on. So at any point of time I have some velocity which I know because I know this curve. So this curve tells me the velocity at any point of time. And then we see here that if I have an impulse at this point, then the velocity generated at this point is v by 2, right? So now if I am interested to know the velocity at this point, I have to look backwards that whether there are any impulses before this instance of time. For that I have to flip or reverse this curve like this. Okay, so this is the flipped, horizontally flipped impulse response. Okay, so this is just the flipped version. Okay, it's just flipped or reflected along across the y-axis. Okay, flipped. This is the flipped impulse response. So now if I am interested to know the velocity at this point or here in this curve at this point, I have to check backwards whether there are impulses before this instance or not. And I see, yes, there is one impulse which is here before this instance. So I am interested to know the velocity at this point. Okay, so at v equals what at this point, and I put this template, this piece of paper which is the flipped impulse response, and I see yes, there is an impulse here, and say if that the height of this impulse is, for example, 1.2, right? Now we know that if here I have an impulse of height 1, then at this point I have a velocity of say v by 2. Here you see that, okay, say this is the v by 2 point. Here you see that here at this point I have an impulse of 1.2, which tells me that okay, the effect of this impulse at this point will be v by 2 times 1.2, or in other words, at this point the velocity will be the product of this impulse, the height of this impulse and the height of this flipped curve or this flipped impulse response at the same point here. So that tells me here the velocity will be 1.2 times v by 2, where 1.2 is the height of the impulse at this point and v by 2 is the height of this velocity curve at the same point. Similarly, if I am interested to know the velocity at this point, okay, so I have to then put this template, this flipped impulse response at this point, right? And now I see that there are two impulses behind this instance which overlaps with this flipped template. One is here, you can see it, it's under this line, another is here, right? And say the height of this velocity here is about say 0.7 v, and the height here is say about 0.1 v, and say this impulse, it has a height of 0.8 and this is 1.2. So therefore the velocity at this point will be 0.8 times this height, which we said 0.7. So this will be 0.8 times 0.7 plus 0.1, which we said it is 0.1 times 1.2. So plus 1.2 times 0.1, which will be equal to this is, let me say, something like 0.1, this is 0.12 plus 0.056, which is equal to 0.176. Okay, so that's how we can compute the velocity at any instance by looking backwards in time and using this flipped template of impulse response. Now at this point I would like to define some new terminologies. Okay, before that, observe that the impulse response or the velocity response of the rocket starts after or from the instance when the rocket is ignited. Definitely, I mean, the rocket cannot have any velocity before the rocket is ignited, because physics says effect can never precede the cause. The effect must occur after the cause, and here the cause is the ignition of the rocket or the burst of the engine, and the effect is the velocity. So it must occur after the cause. But in some case we may have an exception, and I'll give you an example. But before that, let me just define the term causal, C-U-A-S-L, causal system. So a system is said causal if it obeys this kind of cause and effect relationship, cause happening always, effect happening always after the cause. In other words, a system is causal if its impulse response is 0 before the impulse. So we define it mathematically like this: a system is said to be causal if, or double F if, this means if and only if h of t, you may recall that h is the symbol for impulse response, as it is commonly used in electrical engineering and control system. If this is equal to 0 for all t less than 0, right? So if there is no response before the cause which occurs at t equal to 0, then such system is called a causal. So a system being causal means ht is 0 before t equal to 0, and if this is true, then we call that system is a causal system. So this is an if and only if condition, or this is actually a definition. Okay, but there can be exceptions. Let me give you a practical example. You probably remember the candidatal that we discussed before. So what was the candidatal? So the candidatal was an example of a discrete system where every Sunday I used to get some money from my parents, and then I used to buy some candies with that money, and I used to consume them in the days following the Sunday. Or again, when any relatives or any visitors used to visit our home, they used to give me some money as gifts, and I used to buy candies with them and I used to consume them. Again, the pattern was similar. So if this is Sunday, I used to get some money. With that, I used to buy 16 candies. 16 candies for each rupee, each 1 rupee, and I used to consume half of them. So 16 on Sunday, one day I used to have half of them, 8, next day 4, 2, and so on. Now I found that okay, with this rule, so Sunday, this is Monday, Tuesday, Wednesday, Thursday 1, Friday I have nothing. This is Friday, I have nothing, and this is a very bad day for me. Saturday again I have nothing, 0. So what I used to do, I used to go and borrow some candies from the shopkeeper. The shopkeeper knew me very well because I used to purchase these candies regularly. So he used to give, I used to lend some candies beforehand, because he knew that the next Sunday I'm going to pay him back for those candies. So what I used to do, I used to borrow some candies on Saturday, and therefore this impulse response, which you may call it, which is the number of candies over each day, used to look like something this. So if this is Sunday, here I used to get my money, 1 rupee from my parents. So this is the impulse, excitation, and the response used to look like something like this. So I borrow, say, 4 candies on the previous Saturday. So this is the Saturday. So I will have 4 candies, and on Sunday I will buy the remaining 12 candies. So Sunday I should have a total of 16 candies, but I will already consume, say, 2 candies on Saturday. So on Sunday I will have not 16 but 14, and then on Monday I may have 8. That depends on my choice, how many candies I'm going to consume each day. So my choice was like this: 8, 4, 2, 1, 0, and then again on next Saturday I'll have 4, because I knew impulse is going to come on next Sunday. So this is another impulse, but I will borrow the candies beforehand, before that day. Okay, so then this is the impulse response, and it starts before the cause. Okay, so this type of system is called non-causal because it doesn't obey the cause and effect relationship. I used to borrow my candies from the shopkeeper before I get the money from my parents. So such system is called a non-causal system. However, if you just think of it, you will realize that this graphical method 1 and 2 both remain valid even if the system is non-causal. Yeah, I have to obviously satisfy the other constraints like the linearity, which means proportionality and homogeneity, and time invariance, definitely, but whether it's causal or non-causal, if you just think of it, it doesn't matter, and we can safely apply graphical method 1 or 2 to estimate the number of candies each day, or in this case the velocity. If the rocket is by some chance non-causal, the velocity of the rocket using either graphical method 1 or graphical method 2. Now, convolution, this is a very general mathematical idea which applies to many different branches of science and engineering and even other disciplines other than science and engineering, including economics, for example. And the basic idea which I would like to stress on again and again is the fact we always have a cause which could be an impulse, and so this is the excitation curve, across the time. So there are causes and there are effects of those causes, like this cause can be a gift from some of my relatives and the effect can be the candies that I have each day after that or before that. It can be, so this is effect in general, effect over time. It can be, as we have seen, the velocity of a rocket if this excitation is the gas being thrown out from the jet engine. Okay, here this is an example of a discrete time system, discrete because the values are valid only for a discrete, a set of time and not for all time. So this is valid for Sunday, Monday, Tuesday, Wednesday, but not for Sunday and a half, Monday and a 3/4. Those are not any meaningful words at all. But here, this is a continuous time system because the velocity is valid for t equals 0, t equals 1 second, t equals 1.5 second, 1.5983 second, and any such thing. So this is a continuous time system. And this is a discrete time system. We can have a lot of examples of these convolutions. We can think of many physical systems. Let me try to give you some or make up some examples for you in my mind. For example, think of a capacitor, a leaky capacitor. So we have a set of parallel plates with some dielectric sandwiched between these parallel plates, but this dielectric is not perfect, so therefore some amount of charge can leak through it, which we can model as a resistance or conductance in parallel to this capacitance. So this is C, this is, and some conductance or resistance R. And now, okay, let me take this as my reference potential or ground potential 0. If I give some charge at the other point, at the other terminal, suddenly, if I give Q amount of charge suddenly, then instantaneously the voltage here will rise up to a value equal to, so the voltage will be equal to Q by C, and after that this voltage will drop or decrease slowly. In this case again it will be exponentially decaying voltage, so voltage goes up to V instantaneously when I put this charge. So I take some charge somewhere and I put it here suddenly. So if I do it, the voltage goes up suddenly and then drops exponentially. We can show that this is exponential with some time constant depending on C and R. We'll do it thoroughly in a later video. In fact, we'll do a lot of examples of these convolutions related to electrical engineering, because that is our course is focused on. But let me give you some other examples today, which is not very necessary for your course, but it's good to know, to have some idea. Let me think of another situation where, say, I have some heat sink. Say basically this is a large block of metal, maybe copper or some good conductor which can store heat, and say I have it on top of a beaker which contains, or where we can put some chemical, and when these chemicals are mixed in this beaker, they react with each other, and the reaction is, say, exothermic, and the reaction takes no time, so the reaction happens instantaneously, and this beaker is thermally sealed, so heat cannot go anywhere else other than to this block of metal. So as soon as I mix some chemicals, the result of the exothermic reaction is that some amount of heat is being given to this heat sink, this metal block, and then this heat sink can radiate this or pass this heat by means of conduction, convection, whatever it is, and then the temperature of this heat sink goes down. So again, when the reaction happens, that's the cause. If the cause occurs at this instance, the temperature, this is the temperature versus time, temperature goes up and then goes down slowly. Okay, so once again we can think of this as being the impulse response, and then if we mix this chemical again and again at different instants of time, or slowly, gradually over time, then what will be the temperature of this block, we can compute using the method of convolution. So this is an example where the method of convolution is applied, but not in electrical engineering, but in general, maybe in chemical engineering, or maybe in physics, of course. Again, we can think of something which is not really physics or engineering at all, but maybe some social science. Say we are thinking of the exchange rate of, say, dollar to rupees or rupees to dollar, and the exchange rate varies over time. So time versus exchange rate. Okay, and then this generally have a noisy pattern. Maybe if it is dollar to Indian rupee, then this is nearly around, I think, 60 or 65. And then there can be some political turbulence or economical turbulence which may happen at some point of time, which you can think of as the cause or excitation, which may suddenly cause this dollar to rupee conversion rate to go up suddenly. So here this will, from 60 or 65, this will go up suddenly to a higher value, and then it comes back to its normal value slowly over time. So once again, this is the cause, this is the impulse response or the effect. Now this type of systems in social science or in economics are not strictly linear. They are not linear, they are not time invariant. Okay, so strictly speaking, we cannot apply the method of convolution, but yet in many situations people have used this method of convolution to approximately have some estimate of how the things are going to vary over time, how the exchange rate is going to look like over time. So we can do some approximation maybe using the convolution, but again, this is not a physical system, so they are not likely to be linear, not likely to be time invariant, unlike this physical system of capacitor resistance, where this is more likely to be linear, or we can model them to be linear, but these socio-economic systems are not strictly linear, yet this is an example of convolution, and we can do more modification to have better approximation in this case. We can also think of, say, weather forecasting. Okay, so next example could be weather forecasting, where we may observe some cloud or some weather turbulence on some day, and then we can forecast the probability of, say, raining or storm in the days following that day, which may have some pattern. Say if I see some cloud on this day, maybe the probability of raining in the following days is something like this. Again, we can use the method of convolution in this case. So the idea or my main intention of giving these examples in this video is to motivate you what convolution is, how we can graphically find the solution of convolution by adding up the effect of individual causes, where the causes can be either a sequence of impulses or it can be a continuous function, in which case, as you have seen in the previous video, we chop the continuous excitation into small pieces and we think them as small impulses and we add the effect up. So this is the idea of convolution. In the next video we will solve some concrete example to enhance our idea on this. Thank you.